had my assignment in my folder, and I think I forgot to put it in my...
Yeah, if you want to turn it and bring it later, yeah. If you want to bring it in, yeah, fine.
I mean, it's done.
Yeah, it's okay. You can do it. So do whatever you feel. If you want to bring it, that's fine. And bring it in, put it in under my door in my office is good, or in my mailbox.
Okay.
In my mailbox.
All right, I'll do that.
Okay. Yep. Okay. Okay. Some of you may know that the important event today is the NBA basketball game where the Nets and Miami are playing tonight at 7 o'clock, and the Nets have been looking really good lately, except they got stomped twice in a row by Miami, and they're coming. But that was at Miami, and now they're coming to Meadowlands to play the third game. This may be like a thumbtack. Some of you may, there's two reactions. One or two of you will resonate with this, and the rest of you will think I'm totally crazy, but it's not. But the context may be a little strange. But anyway, there is this basketball game tonight. And you might see or hear somebody saying what the odds are. And so I want to start by, we're going to first talk about, so a bunch of the topics for today, so this is sort of the goal. Our goal, and this is you could in fact do a course on one or two courses on financial engineering. This would be somewhere in the middle of that. In fact, Ross, who writes a book about everything, right? This is our author. He wrote the textbook for this course. Here's an elementary introduction to mathematical finance by Sheldon Ross. Yet another book. So this is actually pretty good and nice on this topic. It's interesting. So it's actually kind of cheap too. So it sort of follows from this. So actually, if you're interested in this stuff, I recommend this book. You could sort of get it for like $30. I just ordered it. I thought it was pretty nice. It's Introduction to Mathematical Finance. So this is this, and you would be, if you get this, you'll be familiar because he's sort of, it's the same style as the Green Book. It's only the second edition. This seems to be pretty nicely done. Okay, at any rate, we want to get to talk about these things, and this is going to connect with okay, so this is last time I went to a lot of trouble about talking about the exponential martingale of Brownian motion and the gambler's ruin problem and so forth. So this exponential martingale of Brownian motion appears prominently in the Black-Scholes formula. So this is going to connect. It may be a lot of strange, bizarre things that are not clear that at least are all connected. But anyway, we're going to try to connect these things. Then we're going to start by this fancy word, arbitrage. We're going to talk about this and explain this. This is, some of you, I mean, many people know about this at an early age. I don't know if I can't think about exactly when I learned, but I didn't know this word. But I certainly knew what this was, and this has to do with this. Okay, so we're going to talk a little bit about betting on this basketball game, which is, in my view, roughly the same as this activity here. So it's interesting how the attitudes about what we think about the respectability of these activities are really strongly tempered. That this is it's not clear what earns the most pay. One doesn't want to put this down over here, but this is somehow, bad and good, right? Okay, but anyway, so what does this mean? So we see that the odds are 5-4 for Miami, or maybe it's often against the Nets. So if it's against so then what does this mean? This means that the probability that Miami wins is 5 over 5 plus 4 is 5/9. That's sort of what they are saying. That when you say the odds are 5-4 for Miami or against the Nets, this is reflecting the ratio of the probabilities. The probabilities, this is 5/9 to 4/9. So this is the probability that Miami wins. That's to say, if these are the fair odds, the probability that Miami wins should be 5/9. So when you see 5-4, if the odds are even, for example, if the odds are even, that's like a fair coin toss, and the probability is a half. Even being 1-1 is 1 over 1 plus 1. So when even odds means it's probably a half. Okay, but this is there's a natural thing here about the main point of this word here, arbitrage, is there's a natural thing about probability and no probability. So part of this idea is that you think about this not in terms of knowing the probability, but just in terms of the betting. So if these odds are given, so you might somehow read in the newspaper or hear at some place that these odds are given. What that really means is it means the following, that if you bet, if you bet 5x on Miami or 4x on New Jersey, you're going to win 9x. In other words, if you bet 5 on Miami, that's you pay 5x of any amount, 5 million. You pay 5 million. If Miami wins, you get 9 million, and if they lose, you get nothing. And if you bet 4 million on New Jersey, if they win, you get 9 million, and otherwise you lose it all. Bet, and X means you could do any amount you want, so whatever, it's sort of proportional to what you. This is you win if you bet on Miami, you get 4 more back. That's the 5-4. You bet 5 and you get 4 back, or you bet 4 and you get 5 back. This would be if you could bet either way on this odds. So odds, this word, in one sense, is interpreted that the fair probability should be this. But actually, when you bet, there isn't any probability given, right? What really means is, this means that if you bet 5x, you're going to win 9x. That's what the actual meaning is. Doesn't mean if the probability of Miami winning is more than 5/9, then it would be to your advantage to bet on Miami, because you're going to you're going to get this gain more likely than not. But I mean, the point is, so what the gambler's thinking is, well, is the probability really 5/9? If it's exactly 5/9, it's sort of a fair bet. You might bet or not bet. But an ideal situation is where you know something, you happen to have seen that Jason Kidd and Richard Jefferson and a bunch of these guys are in a car and they just got in a car accident. And you saw that. You were on the highway and you saw that. And they're okay, but they're not going to be able to play tonight. And you know that. Nobody else knows. So the first thing you do is you know now that the odds of the Nets winning in that circumstances have dropped to like 1 in 10. So you rush and quickly bet on Miami, whatever it is, because you know that whatever the odds are, it's not correct. You bet a lot. Okay, that's sort of... Now, the thing that you might be... Okay, this is just... the odds really mean that it's offering you a situation where you bet a certain amount and you win. That's actually what the gambler is telling you. If you give me this much money, I'll give you this if you win, and you get nothing if you lose. The probability is only occurring if it's fair. The inference, if the odds are really correct and accurate and fair, then this is the probability. So it's natural. I mean, there's a level, this is like the course. It's natural. The odds have a meaning precisely as if you want to put up some money, and whether you win or lose, you're going to get this payoff, depending on. That's what the odds are really telling you. The obvious thing to do in response to the odds is to have a probability model and think about what that means. But in some sense, the odds really mean if you bet this much, this is what you win. And yet, this is the probability sits in the background. Okay. Well, now the thing that the reality is, there's a reality that you would see that I guess I'd see. So the odds are, here's what you see quoted. If you want to bet on Miami, it's 5-4 for Miami. If you want to bet on New Jersey, it's even. Now, what I mean is actually, when you want to go gamble, you actually get quoted different odds depending on which side you bet. It's not the same. It's not fair. There's a gap. In other words, if you bet both of them, you'd lose. That's how the guy who's doing the gambling guarantees he's making money. Okay? So that if you bet on Miami, so what do you bet and what do you win? If it's 5-4, if you bet on Miami, you bet 5 and you get 9. But if it's even, you bet 5 and you get 10. Now, so that this isn't really fair, and the point to think of is here is if you are the person offering these bets, and you can offer it this way, you can guarantee that you're going to make money. This isn't an issue. The gambler, the person who makes these bets may win or lose. The person who offers them, if they plan this right, can guarantee that they, for sure, lose nothing. They win. So what does the gambler do? He's going to get, let's say, 5x, 5y. He's going to get 9x and 10y. In other words, he collects 5x. There's lots of people bet 5x, various x's, and lots of people bet 5y. So this is the total amount bet on Miami, the total amount bet on New Jersey, and this is the total winnings. So what he does is he makes sure that what he has to pay out, the winnings, is just one of these. So he sets, let's 9x equal 10y, y equals 9/10 x. Then this is 9x, and this is 9x, right? So no matter what happens, so the guy sets it up so that the payoffs in these two cases are the same. No matter what, he's going to pay off 9x. He's going to make sure x and y are such that this is true. So if this is true, this is 9/10 5, times 9/10 x equals 9/2 x. So he's going to collect his bets and take bets in such a way that he's got 5x bet on Miami and 4.5x, do that right? Okay, 4.5x bet on, so he's taking in 9.5x. He gets 5x bet on Miami and 4.5x bet on New Jersey. So he's sitting there collecting bets, and he just takes these bets as long as he tries to balance this out. So he's got 5x here and 4.5x here, so a total of 9.5x taken in. So like it would be nice if x were a million. He's taken in 9.5 million. But he makes sure that it's 5 million here and a 4.5 million here. Having done that, he pays out 9 million. 9.5 million, put this here, this in, 9.0 million out, 500K in pocket. Good, right? So this is a nice job, right? You don't, this is the casino, various things, you can do things like this. So the guy who's offering these bets, if he controls, then you hear people of laying off the bet. They're making sure that this balance is right. So no matter what happens, they're going to win. Because they've got, these odds are such that they don't balance out. It's not the same odds, and it's always, the difference is in favor of the person offering the bets. If you're the gambler, you may win or lose if you make one of these bets. If you're lucky, you win either way. The gambler wins for sure, and on average, everybody else loses a little. It's just like the lottery. When you play the lottery, you might win a huge total, but whoever runs the lottery wins consistently some percentage. Like lottery's pretty good. Maybe they win 50%. So the people enter the lottery, they award prizes, and half the money taken in is used for something. Right? But it's just revenue. For sure revenue. Okay. Now, this is the situation looks, this is sort of the standard situation is, well, what is it for, there are several perspectives. One perspective is, the gambler, you're going to make a bet, you win or lose, and there's a risk here. You're going to win or lose. The person who is offering these gambles can be set it up so that they never lose. Now, let's shift to the situation so that the situation might not be so bad for the gambler. As we've had it before, the gambler just is lucky or not and wins or loses, but on average, the gamblers lose a little bit because they're taking it in. So suppose, here's a different situation. Suppose actually you could, it's not that hard to do, you could simultaneously be as a gambler in Miami and New York, both. So you might have, in Miami, you're going to have odds. So I have something here. See, let's see. In Miami, if you want to bet on New Jersey, it's 5-3. Miami, if you want to bet on Miami, it's 2-1. Miami. If you're in New York, it's even. New Jersey is even, and Miami is 5-4 in favor of Miami. Now, these are set up in such a way that the person who's offering these bets in Miami, if he balances this out, he's going to win for sure, just like before. And the same thing for the people offering the bets in New York. They win for sure. You can analyze the same thing for each of these separately. However, now, you as a gambler actually have an opportunity. And the obvious thing, this is set up, it's trying to set up for what would be the intuitive thing. You know that in Miami, people are really thinking Miami's good. So what you'd want to do is you'd want to, in Miami, bet on New Jersey. And in New Jersey, you'd want to bet on Miami. because that's sort of like against the hometown. So if you could do that, and the odds were like this, so this you would have, you're going to bet this one and this one. So you're going to put, some million here and some million here and see how you do. But now you are the gambler. You're not the house. You see these odds in Miami and these odds in New York, and you're going to take advantage of it. So you think, just think about what's happened here. If it's 5, let's think what you do. So here's the two you bet. In this case, you're going to put 5-3 on Miami. Means if you bet 3x, you're going to win, if you do, 8x. This is betting on New Jersey in Miami. That's this one. If you bet on Miami, which is going to be in New Jersey, 5-4 favoring Miami. So that means you bet 5y and you get 9y. Same kind of idea, but this is now the gambler. It's us, the gambler, not the house. So it's a lot more appealing. It's, a little individualism here. It's us are going to win. If we can make this work, we're going to win. Okay, you do the same thing. You make sure only one of these is going to happen. So you make these equal. 8x equals 9y. Y equals 8/9 x. You end up losing vastly when your arithmetic is wrong, right? You see, I do all of this stuff, figure it all out, do the arithmetic wrong, put down my 10 million, and get nailed because I did the arithmetic. Okay, so if I did this right, this then becomes 8x and 8x. So we win 8x no matter what. What do we pay? We pay 3x and 5 times 8/9 x, 40/9 x. That's 4 and 4/9. That's altogether 7 and 4/9 x. Good. X equals million, just like before. X equals million. So we pull out of our Columbia account, right? We pull 7 and 4/9 million out of our Columbia account. We put 3 million on New Jersey and Miami, and we put 4 and 4/9 million on Miami in New Jersey. We bet a total of this. We put the right amounts here, but we get 8 million back for sure, no matter which one wins. So we get 5/9, 5, 5, 5, 5, 5, 5, and 56 cents, rounding it out. Win. For sure. Nice deal. No risk. You solve the problem. This is the thing that in finance, you think that you're solving, there's various levels. You could be worried about the probability. One way is to get, the ideal scenario is to get things so that you've eliminated all risk. You win for sure. So if this happened, you would then, if you could, you'd have some problems carrying this out. You have to have 7.4 some million to bet in order to make 5/9. So you're making 5/9 out of this is 60, 63, 67/9, and you're getting 5/9 back. So you're making money at around 6% on this operation. Not a huge amount, but you need to have the money up front to make the 6%. But you make 6% not over a year, but in 3 hours or whatever it is in basketball. You make 6% in 3 hours, but 6% of arbitrary input. So if you could collect input from your friends, you get 6. It's a good payoff. Okay, this stuff is the same. Okay, this is the point here. Some of the finance is exactly the same story, but it's a little different. It's okay. We're in the stock market. Okay, so the model Now, this sounds, okay. We're now shifting gears to the proper world of finance. Keeping our 555K there to remind us this is worth thinking about, okay? So now we're in this thing, well, we have a stock. Okay. None of this crude gambling. We have a stock, current price, $100. Now, this model we're going to talk about is, what is that? Well, we're going to talk about an option. But this, we're going to simplify this to think of the stock is here it is at 100, and we're going to start off at time 0, and then there's going to be a later time later, and that we're going to assume that the stock is either going to go up to 200 or down to 50. This is kind of like finance. This is multiplying by 2 or dividing by 2. But I haven't said with what probability. You might think, if these are really your possibilities, I mean, this model is crude. This model is really simplified because I'm specifying that these are the 2 outcomes in the future at some time. That's not very realistic. This is actually how the finance books start, and this is a convenient example. This is like in Ross, is like this. And we have an interest rate, so when we do present value, we're going to have an interest rate R, but it's discrete time. So $1 at 0 at $1 at time 1 has a present value 1 over 1 plus R. So we have a discount. So that's a factor in this. Now there's this thing, and you could buy this stock. And the kind of point of view is you could buy any amount of this stock. So it's like the bet that you had before. You could put X on here, and if you put X, it comes here, you get 200X or you get 50X, right? You either win 100 or lose 50. But you can put any amount X, just like in betting on the Miami and New Jersey. You can put X here, and then you're going to win or lose. But, okay, now you're offered another bet. This is where the point is it's essentially just the same thing as betting on Miami and New Jersey in New York and Miami. You're now offered not just this bet. You can buy as much as you want or sell at X of this, and you're going to get this. But you're now offered a second bet. Your second bet is an option, and it'll be a call option as opposed to not put. Call option is an option to buy at time 1 for 150. And you can buy as much of this as you want. So you could be, that means that here, so what happens in this option? This is important. What happens here? The rule is you don't buy any stock. So this point of the option is you're inventing a function of the stock, and the rule is that if you're going to pay some price for this option at this time, stock's 100, you pay some price, and you have the opportunity but not the obligation to buy this stock at this time for 150. So obviously what's going to happen is when you get to here, if it's gone up, you're going to buy it for 150 and sell it for 200 and make 50. And if it's gone down, you just don't buy it. Right? So you lost your original price. So that's the option thing. So that's an option is kind of nice as it changes what's happening. So the option in the same scenario, the option, you're paying some price here, and then you're going to get plus 50 or 0. So the option outcome here, If you think of this as your outcome, it's plus 100 or minus 50. So this is the stock. The stock may go up, it may go down. You're facing risk of up or down, winning or losing. You could win a lot, lose a lot. Here, you can only win. Because if the stock goes down, you don't buy it and sell it again. You can only win. You're either going to win 50 or lose nothing. But you pay a fixed price for this opportunity. Fixed price. But the nature of the thing, of the risk has changed. Here, this is just specific numbers. There's an opportunity to win and a risk of losing. You could, whatever you bet, you could have lost it all. It might not just be these opportunities. You could go down to zero. So you have when you buy the stock, it could go up, it could go down. There's a lot more risk. If you buy the option, you pay a fixed price, which hopefully isn't too big, and you lose that. That's you've paid. So if this happens, it costs you this fixed amount. But you know up front the worst. The worst that can happen to you is you will lose this, that you paid for it. If this happens, you'll get, this C better be less than 50. Right? And it's got to be positive, otherwise you'd get it. But so the C is going to be somewhere between 0 and 50, and hopefully it's something like 10. So you say, oh well, for 10 I have some chance of winning 50, and at most can lose 10. So the appeal is the downside risk is reduced. You know in advance precisely what you paid the cost. That's it. It's only positive after that. You're either going to lose your initial investment, or you're going to win something. And in the stock market, it's better than this because there's opportunity might go way up. And then you're going to get all the upside. Whatever upside is there, you get, but the downside is restricted to the fixed amount that you put in at the beginning. So it's kind of appealing. However, at some level, this is exactly the same as the previous problem. You've got two gambles. One approach to this is to interject probability right away and analyze this and make probability models. So the kind of thought would be, well, here I am here, and if the stock could really only do these two things, there's some probability that it does this and this, and I could figure this out. This ought to be fair. So this is an inference that this ought to be fair, and I could figure out P so that the expected value is 0. So actually what's happening here, let's think of the return if that was the case. Expected return. So let me do it without doing this. I'm going to get P times 200 plus 1 minus P times 50. And then I have to discount that. That's in the future. And then I'm going to subtract 100. And so I would say if I want my net return to be 0, I think of it as fair. I set it equal to 0, and I have P times 150 minus 50 equals 100, 1 plus R. Am I getting this? Now I'm bound to get this. P times 150 minus 50 over 100, 1 plus R. P equals 50 plus 100, 1 plus R. I do something wrong probably. P, 1 minus P minus 50, 100, something's not quite right here, right? Over 150. I did something wrong. Let's see. P times 200, 1 minus P times 50, 1 plus R, minus 150. Okay. So if I equals 100, 1 plus R. Okay. P 150, 50. Something. What did I do? That's better. 50, 100, plus minus. That's okay. Okay. 150 plus 100R over 150 1 plus 2r over 3. Okay, all I did was, okay, this is where r is this interest rate. So all I did is figure out what p here would make this fair. I could then stick that p in over here and find out what the cost should be. Okay, that's one way to approach this problem, is to think, well, all these stock gambles, they all should be fair games. That's kind of somewhere is going to appear in this story that's a reference point. Of course, you want to keep in your mind the fact that that may not be true. It's not so good. So this is just one way of thinking. So that's that. The point of this logic is, if I specify p, this is p down here, I can now plug the p in over here and make sure this is also fair and pick c. So I know what the cost should be. But instead of doing that, so let's try use this. Instead of doing that, you do just like we did in the previous gambling example. You consider betting some amount on this and some amount on this and see if there's some place where you can make money for sure. So if you suppose you bet X on the stock and Y on the option. So your return is going to be 200x plus, wait, now the return, we're going to have a look at the return. There's if 200, if 50. We don't average. So now no P. We don't try to figure out what the probability is. We're just going to do it contingent on all the cases. So we're going to say, well, if the outcome is 200, what happens? And if the outcome is 50, what happens? Just like we're going to find that. So if we look here at 200, we're going to see that if it's 200, I'm going to have 200x over 1 plus r minus 100x. And down here, I would have had 50x over 1 plus r minus 100x. That's the result of buying x shares of the stock. Over here for the option, I have as well plus 50y minus 50y over 1 plus r minus cy. And down here, I have minus cy. Right? I've made I invest y. I buy y options, and I get 0 in this case, and I spend cy, and so I spend this at time 0. Okay. Okay. Now, let me think about how do I want to well, let's see. So so I can sort of I have the return and the cost. This is the net return. If I just do the return, I have 200x 1 plus r plus 50y 1 plus, and then I have down here 50x over 1 plus r, and then over here I have minus 100x minus cy. Right? This is the cost, and this is these returns. So what I'm going to do is choose these two, just like before, I'm going to make the returns in the two cases equal. These are the positive part. The cost is the same in both. If I make these equal, so I'm going to have 200x plus 50y equal 50x. So y equals minus 3x. That means it's this return is 50x of 1 plus r, and then this is, so then no matter what, the return is 50x over 1 plus r minus 100x minus cy. I've made the return, the positive part, the same in both cases. I've made it 50x by choosing this. Okay. So the net return, I've got the subtracted there. I get the 50x and then minus 50x over 1 plus r minus 100x minus cy, but that's plus c 3cx because y has been made to be minus 3x. So I've got this net return. Now, I've got sitting here y is minus 3x. So there's three possibilities. This net return could be 0, positive, or negative, right? And this thing is, let me write it this way, 50 over 1 plus r minus 100 plus 3c times x. So this quantity could be positive, 0, or negative. Well, we haven't figured c out. If this is positive, you make x huge, and that's your payoff, right? If this is positive, you make x as large as possible, just like we would want to have made those bets as large as possible. Because if this is positive, x, we can make x large and win. If this is negative, we can make x negative. So that means this is saying if x is greater, so what we're doing here is if x is greater than 0, we're buying the stock and selling the option. On the other hand, if y is greater than 0, we reverse these, right? And the assumption here is that there's a market, just like in that betting, you assume you can buy or sell either one. You can buy the stock, sell the stock at the same price. There's no transaction cost, there's a market, you can buy as much as you want, so you can buy or sell the stock at X, and you can buy or sell the option at Y. I mean, the amounts. Any amounts, negative, positive. So the point of that is, in order for this not to generate free money, this needs to be a constant. And that forces the value of C without assuming any probabilities. We're only assuming that these two gambles are such that there's no free money. You can't choose a mixture of these two things and make money for sure, which is exactly like, which forces, the same reason forces the odds on sporting events to be the same throughout the country, right? Or to be consistent, that they don't permit you to bet in Miami and New York. If they do that, they've messed up, because you would indeed do that and there'd be free money for the gambler. So if you saw that. In this same way, following this reasoning, you would see that C is such that C equals 100 minus 50 over 1 plus r, whole thing divided by 3. And then this is 0 no matter what. And there's no free lunch. And when it isn't 0, that's arbitrage. Arbitrage is the fancy word for making money without doing as much as, free money without any risk and so forth, right? So the assumption here is The reasoning is, instead of thinking probabilistically and introducing a probability that you don't know is real, you reason that you would have to make C this price, otherwise it would be free money. That's assuming this particular opportunity, which does play a key role. I mean, the fact that we have only two outcomes in this case greatly helps. Things are a little more complicated in general, but this is a fundamental principle that's going on in finance. A lot of finance reasoning is based on thinking that prices should be such that there should be no arbitrage, that there should be no free money. Because if you could buy and sell two different things and combine it in such a way that you just guaranteed money, that thing must not be right. So therefore, you're using this logic to say, in that situation, this has to be zero and forces C. Otherwise, people could make money without, whatever, free. So you don't, that forces the C, as opposed to what we had here. Here is, this fair price does that too. If you do the fair price, it'll turn out to coincide with this. That also forces the only way to make sure this, if there is a probability, you're going to want this to be the probability. But that's secondary. I think that one of the main ideas in financial engineering is reasoning from arbitrage as opposed to just computing expected values. And this kind of captures that. This example captures the fundamental reasoning. Okay. Now, okay, that's supposed to be that's the story. Now we want to get to connect this to. We take away our winnings. That was too bad to take away those winnings. It'd be nice to get winnings like that. Okay, now we want to get to Black-Scholes, and part of Black-Scholes is this same story repeated. But okay, so let's see. We're now. Okay, so we're now looking at the black. We want to look at this. And here we're using geometric Brownian motion. And we're going to use the exponential martingale. Now, the main point is maybe this. What was wrong with the last example is it was very unrealistic. You had the stock, and the stock could only go up or down to one thing. There was one time period. The model for the stock is totally unrealistic, that it could be two time periods, and there's a future time with only two outcomes, right? Very unrealistic model for the stock. The idea is okay. It captures the idea okay, but the model's unrealistic. So a realistic model for the stock, well, more realistic for sure, more realistic model geometric Brownian motion is the exponential of Brownian motion. Okay? So the price of the stock at time t is the initial price times the exponential of Brownian motion with variance coefficient sigma and drift mu. So this is an exponential with Brownian motion in the exponential. And this is then the exponential growth rate. And this is the volatility. Now, we might be thinking of the present value of the stock. Present value would be e to the minus rt x of t. This is discounting now r, but now discounting continuously. So the present value at t, the present value now of the stock at t would be the price discounted. So there would be a x0 e to the mu minus RT plus sigma B of t. So this is the present value. This is the present value of the stock at time t. We've multiplied by the discount factor. This is the price of the stock. This is our model for the price of the stock. There's 2 or 3 things here now about this. One is, well, why is this a reasonable model? I mean, one part about this model that's nice is there aren't too many parameters. That's playing a key role. There's this exponential growth rate, and there's this volatility, that's the variability, and then there's this discount rate rho. So in this figure, there's what parameters are sitting here. There's x0, there's mu, r, sigma squared, t. Okay, we've got a bunch of things here, right? So the initial price, the exponential growth rate, the discount factor, the volatility, and time. Okay, well, we want to go through now. Now we just repeat where we were before. So we're going to have an option. Okay, so the option to buy at time t for k per share. So this is the price. This is the price per share, x of t, and this is the present value of the stock, each share, at time t. And option is just like before, only it's continuous time. The option is to buy a share at price k at time t. And you have an option but no obligation. So if at time t the stock is above k, you're going to sell it. You're going to buy the share and sell it. You're going to if it's k plus 3, you're going to buy it for k and sell it for k plus 3 and make 3. If it's less than k, you just don't buy it, and you lost the money you paid for the option. So the option is defined just like before, except now time is continuous. Realistically, it's evolving continuously. Time is continuous, and you're sitting at time 0, and you're thinking, I could pay a certain price, C, for this option. And the option, the stock, again, might start at 100, but it's not just going to go to 200 or 50. It's going to evolve according to this, you think, and you're going to start, say, this initial price might be 100, just like before, and the stock moves like this, and you're told, maybe again, that you could buy it at the end of 6 months for 150. How much should you pay for that? That's the question. This is the answer. C equals blah, 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 right? That's the answer here. So this Black-Scholes formula says if the stock price is geometric Brownian motion, and if we discount, so this is the present value, if you have this stuff, what should the price of the option be? And, well, we've added a couple more. There's this parameter. So we've got this parameter. We've got 1, 2, 3, 4, 5, 6 parameters. Actually, one of these is going to go away. Kind of amazingly, the mu is going to go away. So there's 6 parameters, but there'll be 5 parameters. So then this formula is going to be horrendous from some immediate point of view, but actually fairly simple. So you start to think of, you can actually calculate all the derivatives with respect to the parameters. You can start thinking about a concrete formula to tell you what the price should be as a function of all these parameters, which then starts driving tons of stuff just on this one formula. I mean, you're believing that roughly the stock is going to do this, so it gives you an order. Otherwise, the problem is, if we write this down again, the value, what you're going to get from the option. So what's your payoff? It's easy enough to write down your payoff, the value, let's say, the value of the option. This is its value. I'm going to do this. I'm going to say, here's the present value. The value will be, I've got a discount. Here's the price. this is the thing, where now this thing so we make this funny function. Here's the discounted thing, but we've made a function. This is to say that what we get is anything above k. We're going to get the difference between this price and k as long as it's greater. If it's less than k, we get 0. We're not going to lose. That's what's going to happen. Aside from what we're going to pay up front, this is the payout. So this, the payout, the value, say what you're going to get, discounted value, is the discount times the price minus k, the positive part. The difference between the price and k you're going to get, because you'll buy it for k and sell it for this. But if it's negative, you won't buy it, so you get 0. So this is what you've done. Instead of having a stock that's just going up and down kind of linearly in some way, right? It's going up and down. You made this funny function of the price just like before, where you're guaranteed that once you've paid the upfront price, you never lose anything. It's 0. It only can be positive. The question is, what is the expected value of this? Right? That's sort of the meaty probability question would be, well, what do we do this for this course for? If you do chapter 10, you can see how to calculate this. That has nothing to do with finance other than the model fits, right? I mean, if the model, once you buy this model, then you're just cranking out probability to compute this. Okay? Which is in the book. Okay. Let's see. So I want to say something about 10 or 15 minutes of added explanation. What you're going to be spared is the derivation of this formula, which actually is in the book and not that hard. The derivation of this formula. So there's two sort of, okay, we've got this option. So let me summarize what the question is. What and how is, what is the formula and how do you get it? And I'm not going to do how do you get it, so I'm not going to do that. And then why is this a reasonable model is right here. That why really has to do is why do you think the stock might be this? Okay, that's sort of, I mean, it's not why this, but why as here. Because once you accept this, you've got the right thing. And then there's the part about the exponential martingale, and this is getting rid of mu, the drift. This is kind of that's the sort of sophisticated part. Okay, so as you'll see all this in Ross, this is in sections 10.3 and 10.4 in the book. So hopefully, if you're interested, you'll see this there. The first question I want to do is why geometric Brownian motion? So the kind of model that people have in mind is you have the price is to think discrete time. So instead of this, think discrete time and think that the price at time n is the price at time xn minus 1 times some factor. And that it's multiplicative by independent amounts. So that you end up saying xn is x0 times y1, y2, up to yn. Multiplicative. And so these are all non-negative, positive numbers. So you can't go negative. And you're saying that the change is proportional to the price. So that this is a discrete time model that says it's multiplicative. When you take logarithms, of these products, you get the logarithms being the sum of the logarithms. The idea here is that these y's are IID, the logarithms will be IID, this will be approximated by Brownian motion. So the logarithm will be approximated by Brownian motion by the central limit theorem. And therefore, the exponential will be, this will appear here. The idea is you're thinking of a random walk, but it's the logarithms doing a random walk, the logarithms of the prices. Or you think of in the direct prices, it's changing multiplicatively by independent factors. That's the reasoning for choosing this model. That gets you this. And when you're doing the mean and variance of the log, that's these parameters. Sigma squared would be the variance of the log. This is square of this, and mu would be the mean of these logs. Well, and you've got to scale it. So you're doing in this process a little more complicated, but you're doing the discrete random walk is going to the Brownian motion, but that's appearing in the logarithms. So that in the end, the Brownian motion you get that approximates the random walk appears in the exponent. Okay, the idea is you're thinking it's multiplicative. When you take logarithms, it's additive, and that explains this exponent. Okay. Now, a key element is I have this here. So here's the present value t, and it's x0 e to the u minus. Now, there's two parts here. One part is just evaluating this thing, which is cranking out formulas with Brownian motion. The other part is a simplification. And the simplification comes by assuming there's no arbitrage, which is going to be assuming that this present value, this is kind of sophisticated, but that's to assume that this process is a martingale. Its expected value is going to be the same all the time. It's going to be a fair game. That's a connection to the arbitrage, to be a theorem that says in order to avoid arbitrage, you want the process, the present value process, to be a martingale. So that's the connections to before to saying I want the p's such that the expected value is 0 in those gambles. But now I'm going to make it a martingale, which is going to have the expected value as constant. So I want this process, this is the present value process, I want it to be a martingale. Then you remember, hopefully from last time, that we had this, the exponential martingale of Brownian motion is this. So if you have this exponential of a Brownian motion with some parameter, if you subtract this in the exponent, it becomes a martingale. That's the exponential martingale we used last time. Knowing this is a martingale, you look at this and you say, oh, well, what do I do with these parameters? Well, this tells you that theta is equal to sigma. Therefore, in order for that to be a martingale, mu theta is sigma, so therefore theta squared, sigma squared over 2t has to equal to mu minus rt. In order for this to be of this form, I make this theta, and then this has to be theta squared over 2. So sigma squared over 2t, the t's aren't here, so I end up with mu. Now, did I do boom, boom? I've got this. This has got to be minus, so I've got this mu minus. I've got a minus, so mu is, wait, let's see. Mu is equal to r minus sigma squared over 2. Because I've got this minus sign here as well. So I've got mu equals r minus sigma squared over 2. So this particular step is the one part that's not probability. As such, this step is actually saying that in order to avoid arbitrage, I need it to be a martingale. I have it this thing. So if I need it to be a martingale, that's the formula. I need this. And that gets rid of the mu. That tells us the mu should be this. In other words, the discount rate and the volatility are determining what mu should be. Okay. Now, let me just write down this thing here. Okay. So the price, C, this is the Black-Scholes formula, first step. Okay, this is just illustrative, but let me just discuss what's here. Understanding this is would require a little thought. These things, the phi of x is just the CDF of the standard normal. So this is like on page 81 of the book, right? So this phi of x is the CDF of the normal, and here it is here, and here it is here. So these funny functions phi are just normal CDFs. So sitting here are the parameters x0, r, mu, sigma squared, sigma t, a. Now we haven't got a yet, so we've got to find a. So a looks like log k over x0 minus mu t. Okay, this looks bad and good both. Here is this formula. At some level, this is pretty messy. Okay, but it's extremely concrete. So if you wanted to start working here, you see here's the formula. This is giving you, actually, this is directly computing this expected value. This is just saying, oh, this is geometric Brownian motion. You've got this positive part. You're actually, without doing any martingale yet, you're just calculating it. This is just how to calculate stuff with Brownian motion. The same kind of stuff you did in the homework problems. You do that again here, as in Ross, and you get this formula up here. It's not too hard. Ross derives this on about one page. You're going to do some change of variables. It's a little bit of, it's not really too hard. And you end up with all this stuff here. And here's, in terms of all these, here's these parameters, x0, mu, r, sigma squared, t, k, all these 6 parameters. And here's the formula for what the cost should be. Or what this is actually the value. Now so this actually didn't depend. I've still got mu here. I didn't get rid of it in this formula. The mu is sitting here. It's sitting in A, and it's sitting up here. But all in there are all these. There's the initial price x0. The strike price is the price you're going to pay for the stock at the end, in part of the option. The strike price k, the time, the expiration time t, the growth rate, the discount rate, and the volatility are all sitting there. And you've got this formula. And then in this formula, you insert this martingale. That's where the martingale fair price to make the cost. And that's what the price should be. When you stick in this, and mu drops out. But that's the fair price, is that the last step when you plug that in. That step is roughly equivalent to the discussion we went through at the beginning of the class, that you're arguing that there's no arbitrage. You have to do that. So that's pointing to this. That's pointing to this, that you should make this in order for this to be a martingale, which would be what you need in order to avoid arbitrage. And that simplifies that, reduces the mu out of the problem. There are lots of people doing, making their living chewing on this formula in one way or another, right? You can think about, you're collecting data. Does it fit this formula in what way? And if it doesn't fit, what can you do to fuss around with it, and so forth? So this is the stuff that you're doing in Chapter 10 should be illustrative. You're calculating things with Brownian motion, which is lots of stuff with normal distributions, and that formula is just more of the same. It's not extraordinarily difficult. There's whole books on stuff you can calculate related to Brownian motion. Lots of finance people are doing all sorts of other variants of these kind of problems, which roughly boil down to calculating things like this. You're calculating the expected value of some complicated function of the process. You're actually just evaluating something where this is the process, and here's Brownian motion sitting in here, and you're fussing with it and doing these calculations. In the finance world, if if you do go there, this is what's going to be expected of you to do, is that you will be able to do all the calculations related to all this stuff, meaning lots of things, like doing the statistics, data analysis, doing the computer work, right? The computer, doing stuff with this formula, and so forth. So there's all the kind of optimizing, all this stuff could be done on top of stuff like this. I mean, this is illustrative of issues, of all the issues would be kind of start from this thing in some sense. Well, we have, there's lots of courses here that actually do this, the whole thing, instead of one class that sort of touches on this. But this is nice too. This book, if you're interested in the finance thing, this book is nice as a part that follows naturally from the first book. Lunch. There's a free lunch. Not a free lunch, but there's a lunch. Okay, Tuesday will be a review class here. I will go through the last year's final exam here on Tuesday, or some of it. Yeah.
Is the stuff from today covered on the final?
Not directly. Okay. So my thought is the stuff this week is not particularly covered, but you should be able to do calculations with Brownian motion. So the general thought is that you should be able to do stuff like on the homeworks. The homework should be the guide. Some of the homework problems are not anywhere near as bad as this, but stuff like calculating the expected value of BT1, BT2, BT3, right? Those homework problems are illustrative that just you're starting to be able to calculate with Brownian motion, but not getting too carried away.